Hi guys, today we're going to talk about scatterplots. So a scatterplot looks like this. It's a way to display data. This particular example I took from Engage New York. Um, and this is particularly comparing the age of a citizen with the time and minutes required to solve a word puzzle. So just like X and Y, we have labels, we have data points that represent individual people, um, and a scatter plot can display a lot of information all at once, usually real world data. So the parts of a scatter plot that we look for are the title. So uh, you should be naming scatter plots that mean something in the real world. Axes, so you're going to have your X and Y axis, and you're going to want to label on that axis, okay, this is representing time, and this is going to represent distance. Um, in For scales, what I'm referring to is you need to make sure that, okay, I've said that this is 1 minute, 2 minutes, 3 minutes. So either I can write 1 minute, 2 minutes, 3 minutes, or I should write it down with the label. Same thing with the distance. I should say in meters, I have 10 meters, 20 meters, 30 meters. And then you have data points. Each data point represents a different trial. Now, one thing that people, or two things that people get wrong, is that scatterplots are not always, are not connected. So you can't, if you see a line like this, you should not be doing this. This is not a scatter plot anymore. Now that's called a line graph. So you shouldn't be connecting your points on a scatter plot. And some scatter plots are functions, but not all of them are functions. It is possible to have, say, in this scenario, we didn't in this scenario, but it's possible to have two people with the same age having um, having different times that it takes them to complete the puzzle. So you can have it be a function. You can have, for example, this one each time has a different distance, but it's possible to have a scatter plot that is not a function. When you want to analyze a scatter plot, you should look for four main things. The first thing that you should look for is the form, and what I mean by that is, what does it look like? Does the pattern seem linear? Does it seem exponential? Does it seem like there are clusters, that there's a bunch of data points in one group and a bunch of data points in another group? There could be no pattern, and there could be a pattern other than these, but you should first look and see, okay, does it look linear? Because not all data is actually linear. The second thing that you should look for is, are there any outliers? So we will be talking a little bit later, and we've already seen residuals. You can look at the residual plot in order to determine if there are any outliers. What's the direction? Certainly it's important to know whether this is a positive correlation, so it has a positive slope, or is a negative correlation with a negative slope. Again, that would only be true if it's linear or there's some exponential. It kind of is tied to the form, but a positive correlation is a very different result from a negative correlation. And then the strength, which we usually quantify with what's called an R squared value. R is a correlation coefficient. Correlation coefficient is R, and then we square that, and that will determine the strength of the correlation. So correlation is the strength of the relationship between variables. So if we have a correlation coefficient of 0.9, that's a strong positive correlation. if we have a correlation coefficient of 0.4, that means that it is a weak positive correlation. And if there's none, then there's no correlation. And it is possible to have a weak or a strong negative correlation. Now, I just came up with these numbers as examples. You can have a correlation coefficient of 1 or -1 or negative 2300ths. And this is a scale between 1 and -1 of how strong it is. So we'll look at some graphs and you'll be able to see what they look like. You're not going to have to calculate this by hand, and graphing utilities can do it for you. So let's look at scatterplot A. Let's answer these questions one by one. So what is the form of this? So the form of this scatterplot, it looks pretty linear to me, so I'm going to just write that down. The outliers. There is a point that looks like it's an outlier right here because it looks pretty far away from our line of best fit. Now, how can we actually show this? Well, I've graphed this on Desmos. If you type in, as we did before, a linear expression, it will come up with these statistics for you. And specifically, the residuals are something that you can choose to plot. So what it's going to do in order to plot the residuals is it's going to compare this number, this point, with the line and see how far above it is it. So that point will end up right here, and this point, because it's below the line, will end up right here. So essentially what we're doing is we're subtracting each of the y-coordinates minus what the line of best fit predicts that it will be. So this point, 1,6.4, is ending up at 1,0.164 because it's being subtracted from there. And this point is ending up down here. If we just look at the residuals, which are in orange, then it's very clear to see, okay, most of these points are very close to the line of best fit. The line of best fit essentially is represented by the x-axis once you graph the residuals. Then this point is clearly an outlier because it's so much further away. There are statistical methods to determine exactly what that is, but that's not being done by hand. So that's how we can show that 4,11.7 was in fact an outlier. So it's just a point far away from the line of best fit. So that would be my outlier. What is the direction of this correlation? Well, the direction of this correlation is it's a positive correlation, and you can also see that when it calculated the statistics here, the R value, the correlation coefficient, was positive. And then lastly, we want to look at how strong is it, and that's by looking at the R squared value. The R squared value, I'm not sure if you can read it, is 0.419, 419 thousandths. So that is a weak correlation, and I think part of that is the outlier affecting the correlation. But there is a correlation, and it is weak, positive, and linear. So that's how we analyze graph. Now let's do one with slightly different information. So take a moment to look at this. The first thing that you should notice is that there are two groups of data points. There's a cluster here, a cluster here. So there are clusters. That's what I'm going to say for the form. Now these aren't highly technical terms. Are there any outliers? It's not clear to me that there are outliers, but let's check a residual plot. So once again, I'll type in y1 is approximately mx1 plus b, and it will give me the line of best fit. That seems like a reasonable line of best fit if I plot the residuals. Well, let's see. All of these points seem they're reasonably close to the line. I mean, they're not quite as close as they were in the previous one, but they're all about the same distance compared to each other. So there's nothing that's really far off the pattern. I would say that there are no outliers. The direction here, well, you can see that the slope would be negative. And yes, the R value agrees with us that it would be negative 0.493 is the correlation coefficient. And then, send this to the back. And then the last thing is that the strength of this correlation would be strong. And how do I know that that's strong? Well, it says right here that that's very close to 1. 0.89, 89 hundredths is close to 1. So I want to say that this is a stronger correlation than our original one was. So this is an example of a strong negative correlation with two clusters, whereas this is a weak positive correlation with an outlier. All right, hope that helps. Thank you.